This topic is going to be on security requirements of embedded systems, with a special emphasis on field updates. So I've talked a lot about field updates in other OSADL talks. So this time it's going to be more focus on the security requirement side. Short introduction on my side. I'm Jan Lübbe. I'm working at Pengutronix since about 9 years now. And I'm co-maintainer and initial author of RAUC and LabGrid. So RAUC is a system update framework and LabGrid is for testing embedded systems. And maybe not all of you know about Pengutronix. We are an embedded consulting company on the market since 2001 and have in the meantime published or upstreamed more than 5,700 patches into the Linux kernel and other open source software. So short agenda for today. I'm going to talk about the basic requirements regarding security, the available mechanisms in security area, and then focus on the common obstacles we experience in projects with our customers and what we've seen outside in conferences and so on. And then I'll try to give some concrete suggestions and guidelines how to avoid these pitfalls. So, yeah, to reiterate, why do we need security? That should by now be obvious to most of you. So we want to protect sensitive data, maybe user data. We want to protect intellectual property. So, for example, proprietary algorithms. We want to protect against sabotage and ransomware. That's especially important in industrial control systems and so on. So there can be also safety critical systems where we need to ensure security to be able to provide safety as well. So there are obviously a lot of additional reasons you could think of, but today I think I can summarize this by saying that in the recent years, we've got international standards which describe how to build secure systems, and it's going to be a legal requirement soon as well. There's recently the ETSI, the European Standards Organization, European Norm 303654. It's a standard on securing consumer systems, but it's really recent, came out in 2020. So there are a lot of really good points in this standard, and you can no longer say that not protecting your, not encrypting your communication or not protecting against modification of the software on the device is any longer state of the art. So there's going to be legislation requiring things like that. In Finland, for example, there's a cybersecurity label for consumer products, which is based on this standard. So it's not required yet, but you have to go through a certification before you can use this label. So there's definitely some legislation and push from the government going on. Yeah, so there's basically no longer any way around having robust security in our systems. And if you take a look at this standard, there's points about secure updates, secure communication, secure key storage. You have to minimize the attack surface by disabling network services and so on. You have to ensure software integrity, so things like secure boot. You have to have a process for handling security reports in a reasonable time frame. They give us 90 days as a guideline. So it's no longer as easy as it was 5 years ago, maybe. So what do we have as mechanisms? Obviously, firewalls, as you heard in the previous talk. You have sandboxing mechanisms like namespaces or Linux seccomp. You have containers, which can be a security mechanism. They don't have to be. You have hypervisors and virtual machines, which can compartmentalize your software. You have verified boot mechanisms like DM-Verity or FID images. You have, since many years, Linux security modules, which are optional mechanisms to reduce the access of individual applications in the Linux kernel, like SE Linux, AppArmor, and so on. Then you have hardware root of trust mechanisms in systems on a chip, so you can be sure that you're running the software you want to run. There are things like TPMs, Trusted Platform Modules, hardware security modules, or secure elements that all provide different mechanisms to protect your data or protect keys. There are secure enclaves, so you don't need additional hardware to get similar benefits to TPMs and HSMs. You can use remote attestation to basically ask a remote system if it's verifiably running the correct software. You have hardening options in toolchains, which are easy to use and prevent buffer overflows in many cases. Obviously, there are standardized mechanisms and widely deployed tools to do over-the-air updates or local updates as well. And there are new safer languages coming up, like Python or Rust or Go. And these avoid whole classes of errors like buffer overflows or data races or null pointer exceptions and so on. So taking a step back from the low-level technical details, there are mechanisms you can establish code review practices and coding standards. You will have tools for vulnerability scanning of images or containers. There are things like fuzzing when you have network services and want to ensure that they handle outside data correctly, that the data sanitation works. You have features like telemetry and monitoring for systems in the field, where you can get feedback like amount of invalid logins or any errors that occur, crashes in network services and so on. Also intrusion detection systems, which you can have separate from the embedded devices we're usually talking about, and that can detect port scans or other indications of ongoing attacks. So basically, we have all these powerful mechanisms, and they are well established, and we can use them in projects, and they are used. So why are our systems still vulnerable? So why is this still such a large problem? We can think back at this quote from Bruce Schneier in 2002 in his book Secrets and Lies. It's still as true as it was 20 years ago. So we have lots of mechanisms, and they are better now, but our systems are more complex, and we realize that the problem is usually not the technology, but how we use the technology and which technologies we use and the processes around them. So I've looked at some of our customers' projects over the years and talked to other people in our industry and collected some of the recurrent issues we see there. So each of those is basically enough to cause serious problems. So we have things like customers coming to us and saying, our project is basically finished. We want to sell it in next month or something. And we just need a bit of security. So it's difficult in this situation, as you all know. There are unrealistic schedules. There is time pressure, so there's not enough time to implement these mechanisms as they should be. And in some projects, there's also the understanding from the project management that features and performance are more important than security. So we basically have different objectives that work against fixing or building serious security. So, and even more often, we have the case that in the beginning of the project, there was no threat modeling done. So there is no clear decision which parts need to be protected, what are the expected attack vectors, what are the adversaries, and so on. So this leads to gaps in the security because things have been overlooked, and also in other parts you build unnecessary security mechanisms which protect against threats that are not relevant to your product. So yeah, each of these is enough to cause serious problems in the runtime of the project. And there are still some issues that are less obvious, but still happen very often, and they make it harder to achieve good security in a project. So we start with, there may be resistance to changing requirements during the project. So often at the start of the project, it's not really clear how all the different mechanisms and features are going to be implemented. So over the course of the project, it becomes more clearer, and requirements that seemed initially obvious do not make any sense any longer. So there needs to be a way to change these requirements, often between different teams. And if you don't do that, you get, again, gaps in the security, you get workarounds where one team has to work around mechanisms built by another team, and that obviously causes delays. Then very often you have insufficient communication problems, that different teams don't talk to each other or are not allowed to share code. That makes it difficult for debugging and so on. And often this also leads to wrong mental models how the whole project is going to work and fit together. And this in turn leads to gaps again and unnecessary security measures. So it's important to keep people talking to each other. And we've also seen often that you have, in the beginning of the project, very restrictive security measures. Like you don't have a serial console, you can't log into the system, can't observe it in action. And that leads to a negative feedback loop because the developers want to work efficiently, but the security mechanisms prevent them from doing so. So there's a push by these developers against security measures. And that's, if this goes for some time, it's difficult to get out of that loop and get people working again for security. And we often have missed opportunities if the development team is not deeply involved after the release. So from the field, we can get early indicators of threats, like crash reports or failed logins, IDS events, and so on. And if we don't process these events, or if we don't look at security issue reports from professionals in the community, then we basically miss a lot of opportunities to fix problems early. And obviously, I can't skip about this. So there's often technical debt, and it's often the problem. People know that technical debt exists, but if the pain that is caused by technical debt becomes noticeable, it's often too late to do anything about it, because then it's already such a large problem that you don't have enough time to actually work on it in an efficient way. So it's important to look at this from the beginning to avoid it, to avoid project-specific modifications in areas where we don't need them. We should look for deprecated or unmaintained components and replace them early enough. And also avoid the not invented here syndrome. So don't build new things where already existing tools may do 90%, and then it's better to extend them and upstream that. So what we see here is, again, what Bruce Schneier already told us 20 years ago, that security is not a product, but it's a process. So even if you have a high security system as a goal, bad processes can easily lead to critical issues. So this is not something that can be addressed by individual developers, but that needs to be done at a higher level in management to set the right direction. And I think that in the current situation where we have upcoming legislation, it's a good chance to change these processes, because management is also involved to avoid these legislation risks and so on. So it's a good chance to change these processes for the better. Can also be a marketing benefit, like we've seen with the Finnish cybersecurity label, and can be a chance to improve the workflows in other areas as well. So in the next slides, I'm going to look at some recommendations how you can change your processes to make sure that, make it easier that good security comes naturally. So going back to the threat modeling, that's something you should do at the start of the project, involve all stakeholders, so not just the engineering team, but also management and marketing, and ideally the users as well. So that should identify the assets, so the things we want to protect, and the actors in the system, adversaries, and so on. We need to identify threats and the corresponding mitigations. We need to identify the components in our system, the interfaces between them, where we can add protections between these components. And additionally define high-level goals, so things that are easy to remember during the development. And you should go back to updating the threat model every so often, because attacks change, the implementation changes, you add components, remove them, and so on. And there are some very good tools to help with that. There's from the European ENISA organization a good practices tool. I have a link in the end of the slides, but you'll also be able to Google that. And there's from the OWASP Threat Dragon tool, which is a web-based tool to model basically your system and the threats. And we also have often a misunderstanding in projects where safety is relevant, that there's some conflict between security and safety. But in most cases, there cannot be any guarantee of safety without having security. So you should take a look at what parts can be shared and use the same motivations to push both areas forward. So a big benefit in your system will be if you can simplify your architecture. So you should evaluate the risks and complexity trade-offs of any protection mechanisms. Any complexity you don't have can't break. That's easy to keep in mind. So you should choose the appropriate mechanisms based on their complexity and what the expected benefit is. And that is, again, where the threat model comes in. And you should look at the prevalence and maturity of the security mechanisms you want to use. So, if possible, prefer mechanisms that have been proven in the field. And something to keep in mind as well is that you want to ensure visibility of the security mechanisms for your developers during development. So that helps avoiding black box effects. So that only some of the developers understand how the security mechanisms work and can improve them, and the others see it as not my problem and try basically to work around these security mechanisms instead of using them to help them. And so by increasing the visibility of the mechanisms and events they generate, you avoid keeping this knowledge only known by some few people. So when working directly on the technology, on the software, it's important to establish some baselines. So you want to have a mechanism to have 100% reproducible builds and deployment processes. because this is basically the key to having reliable debugging in the field and being able to deploy targeted fixes. So if you identify a problem and want to fix only this problem and not retest your whole system, you need to be able to rebuild it 100% reliably and deterministically. So that's one part. The other is automated integration tests. I've talked about this in other talks. You want to have a CI system which basically tests every change automatically, runs it on the real hardware to build confidence that you can deploy the software without causing regressions. And it also helps reducing reaction times if some security problem occurs, because you can test much faster than manually. And then there's this concept of renewable security. That's basically your plan B if something goes wrong in the field. If systems have been compromised, or you suspect they could have been compromised, you need to have the way to get those systems back into a known good state without going out in the field and reinitializing all of them. So this is based on a verified boot chain and remote attestation. You can add mechanisms to revoke compromised keys, and you need to have robot protection. So an attacker that may be local cannot reinstall an old system which already has a known vulnerability. So this is a good argument to add something like verified boot or boot authentication to systems which would otherwise not really need them because they're not in an exposed environment so much. So basically your authentication chain starts with the ROM in the system on a chip that is fixed and known good. And that in turn authenticates the bootloader, and each step in turn authenticates the next one. So you basically have a chain of authentication from the ROM up to your application. And only a reboot is needed to re-verify everything. And by having this, you can simplify your reasoning about trust and attack vectors at the higher levels. Because you don't need always to keep in mind what would happen if something was modified in storage and an attacker's program was running instead of my own system. So then there are some ways you can get more of the team involved in the security aspects. And this can be done by implementing a development mode switch. It's something you should think about early in the project. So you basically have a way to install a more open system on development devices. That image would not run on devices in the field because it's signed by different keys. And this allows the developers to work efficiently and look at the system from the inside without always doing individual configuration of security features on and off. So basically you have two different modes, a development mode and a release mode that is compiled into different images, and those run on different systems. And this would also re-enable the debugging aspects. So you can run a debugger, a remote debugger, JTAG, and so on if necessary. And by giving each developer access to the keys necessary for assigning development images for development devices, it's easy for each developer to build modified images to debug problems. And you should also consider a field return mode. So there's going to be cases where systems fail in unexpected ways, and to analyze them, you need to get them back into a development environment and delete the encryption keys for user data, so that is not exposed to developers, and allow booting unsigned code again, so you can build the debug tools for this system. So there's always inherent complexity in these systems, and that cannot be completely avoided, but we can avoid local complexity. This way avoid local maintenance costs. But this means reusing proven and open implementations, things like MQTT, OPC-UA for communication, TLS, Opti for key storage, or FIT images for kernel signing, and so on. So we reuse these components and don't have to manage all this complexity ourselves. And this also applies to the security architectures. So the way we build the verified boot chain, for example, or how to organize our firewalls. That should not be project specific, but reuse existing mechanisms as much as possible. And this also means that we need to question requirements which would require custom solutions. That should also be investigated if the additional local complexity that is caused by that is worth an additional benefit. So by having less customization, we also can think about these systems easier because we can reuse existing experience, and that leaves more time for testing and reviews and looking at the things that actually need to be different in each project. And for the local complexity that remains, you should look at pushing that upstream. So that's a very common idea in the OSADL environment. But I wanted to emphasize it here again. So you should also prepare for long-term maintenance. So it depends on the project, but many of those embedded systems run for 5, for 10 years or even longer. And by avoiding risks of large divergence or technical debt, we can make it much easier for us to maintain these systems for a long time. We should avoid the kernel vendor forks if upstream support exists in the Linux kernel, or out of tree drivers because they lock us in old versions and we cannot follow the security releases for as long as we would need to. So it's very beneficial to have a fixed development and update schedule for the system. So something like every once in a year, update all of the baseline components to be in a state where they are still supported from upstream. That makes it much easier to add security fixes and then release them into the field. But that should not only be done for CVE vulnerability fixes, but more often, so you have basically training and experience with the release pipeline. That makes it much easier and more reliable when you have to do it in a hurry because a critical security problem occurs. And consolidating architecture for multiple projects is also a good way to free more time and attention on security fixes or functionality fixes as well. So by sharing parts of the project or parts of the software stack across multiple projects, we only have to fix an issue once and deploy to multiple project lines. And can share the testing and experience over these multiple projects as well. So when looking at field updates from a security perspective, we have some requirements regarding the update mechanism. Obviously, it needs to support the security mechanisms and not interfere with them. Things like a verified boot, where you have assigned software that needs to be bit identical, that needs to be supported by the update mechanism. And it should also be as simple as possible to handle deployment and development. To do that, the most important thing is that it needs to be reliable and deterministic. So we need to be sure that the software that ends up on the devices in the field is exactly the one we've tested in our lab. And it must be easy to integrate in the development workflow. Finally, it should be built on standard components, protocols, and implementations. So to show how these can be provided by an update framework, I'll use Rauk as an example, as it was specifically designed with these requirements in mind. So to make updates deterministic and reliable, we decided not to use package-based updates. So like you know from Debian or Red Hat-based systems, where you install individual packages, because that's usually requires interactive administration. There can be conflicts in configuration files. You get untested combinations in the field, and it's also easier to affect that by file system corruption, because you usually have a writable file system underlying that. So instead, we use full image-based system updates, where you have basically the whole state of the system in a well-defined way in the update, and that is rolled out into the field, and then you can be sure that what you have tested is actually ending up on the devices. And we built Rauk in a standard-based way. So we have, for the signatures, it's basically X509, the standard signatures used by OpenSSL in the CMS format. We have a squashfs as the bundle, as the update container. It's based on glib, uses the PKCS11 standard for accessing hardware security modules, uses curl and dmverity. So there's as little as possible custom code that needs to be maintained for that. So in many cases, the update architecture of the system does not require any customizations in Rauk, because standard AB updates or bootloader updates are already supported in a general way. So to summarize, we have proven security mechanisms for many use cases that we can use and are using, but the real-world problems are often not the technical ones, but the process issues. So it's very beneficial to look at how to change the processes in a project to improve security. So, and the motivation is getting easier, because we are going to be required to do all these things by standards, by legislation. So it's a good idea to improve these processes and workflows now, to get in early and build this experience. And it can also be a chance to trigger the necessary changes in the processes from the bottom up. Yeah, so thank you for your attention, and I'm looking forward to the discussion.